Welcome to my channel D square plus D. In the previous class, we learned an operation on matrix, that is matrix addition. Today we learn matrix multiplication. And before we come to the definition of matrix multiplication, let us take two students, Meera and Mohan. They wanted books and pens. Let Meera wanted 6 books and 5 pens. Mohan wants 7 books and 6 pens. They make an enquiry in the market in 2 different shops. They find that the first shop, the cost of a book is 25 rupees, whereas the cost of a pen is 20 rupees. Mohan enquires in another shop and he finds that cost of the book is 15 rupees, whereas the cost of the pen is 30 rupees. Now they wanted to decide in which shop they will get the items in a cheaper price. So, if we present this data in a rectangular form, what you have studied earlier, 6, 5, 7, 6. And we know that the rate collected for each item, here it is 25 and 20, that is in shop 1. Whereas in second shop, the same is costing 15 rupees and 30 rupees respectively. If we assume that Meera buys her item from shop 1, then she needs to pay 6 into 25 plus 5 into 20. Likewise, if Meera buys the item from the second shop, then she needs to pay 6 into 15 plus 5 into 30. Now we analyze the second example, that is Mohan. If he buys the item from the first shop, then he needs to pay 7 into 25 plus 6 into 20. Similarly, if Mohan wanted to buy the book from the second shop, he needs to pay 7 into 15 plus 6 into 30. That means they need to pay now 6 into 25, that is 150, plus 5 into 20, that is 100. Here it is 6 into 15, that is 90. Plus 5 into 30, that is 150, and 7 into 25, that is 175, plus 6 into 20, that is 120, and 7 into 15, that is 105, plus 6 into 30, 180. So if we simplify once again, we get 150 plus 100, that is 250, 90 plus 150, that is 240, 175 plus 120, that is 295, 105 plus 180, that's equal to 285. So by looking at this arrangement, we can say that these students, Meera and Mohan, they will be getting the benefit when they buy from the second shop. The way in which we have presented this data, that means we have got the matrices 6, 5, 7, 6, 25, 15, 20, 30, and finally with certain operation we got it as 250, 240, 295, 285. This particular operation we call it as matrix multiplication. In detail, when we take two separate cases, A equal to matrix 2, 3, minus 1, 4 and B equal to matrix 7, 2, 1, 5. We know that A is of order 2 by 2 and B is also of order 2 by 2. Now I need to multiply this A and B. We simply write it as A into B or AB, and that's defined as 2, 3, minus 1, 4 into the second matrix, that is 7, 2, 1, 5. If you recollect the example what you have done in the earlier page, we take the multiplication like this. That means 2 into 7 plus 3 into 1. That it means we have taken the elements of the first row and we multiplied by the corresponding elements of the first column. This process we continue until the columns are exhausted. That means we go to the next one, that is 2 into the second element, that is 2 plus 3 into 5. Our columns are exhausted. So we come to the second line, that is minus 1 into 7 plus 4 into 1. Then going to the second column, we get minus 1 into 2 plus 4 into 5. On simplification, we get 2 into 7, 14 plus 3, and here it is 4 plus 15, and here it is minus 7 plus 4 and minus 2 plus 20. Further, we get a simplified matrix, that is 17, this side 19, this is minus 3 and 18, and its order is 2 by 2. So we say that here the product A into B is equal to 17, 19, minus 3, 18. Now we take a few elements. In general, we see that how the multiplications are carried out. Let A is equal to matrix A11, A12, A21, A22, and B is equal to matrix B11, B12, B21, B22. We know that order of these two matrices are equal, that is of 2 by 2. And we find the product A into B, and that's equal to A11, A12, A21, A22 into the second matrix B11, B12, B21, B22. And we use the principle what we have discussed earlier. We take the elements of the row and we multiply by the elements of a column. We get A11 into the first element here, that is B11, plus A12 into B21. That's over. Going to the second column, we get A11 into B12 plus A12 into B22. We know that the columns are exhausted. Coming to the second row, we get A21 into B11 plus A22 into B21. Moving on to the next column, we get A21 into B12 plus A22 into B22. This matrix is of order 2 by 2. So this is the way we define the product of two matrices A and B. Once again we say that the first matrix A is of order 2 by 2, second is also 2 by 2, and the result what we got, that is also 2 by 2. So in what way we define the product of two matrices? In the case of addition, we know that the addition is defined only when the matrices are having the same order. If A is a matrix of order m by n, B is also of the order of m by n, we say that A plus B is defined. But in case of multiplication, it's entirely different. But this example, it says that if A is of order 2 by 2 and B is of order 2 by 2, A into B is defined. But actually when you look at this product, the way in which we carried out, we know that number of elements in this column, that is there are 2 elements, and that is equal to the number of elements in the row, that is A11 on product that corresponds to B11, A12 that corresponds to B21. In this case, we can say that if you take 2 matrices of the order, say for example Aij, if that is of order m by n, then we can take another matrix that is of the form Bjk, that should be of the order n by p. In this particular case, we see that these 2 letters are same. That means number of columns of the first matrix should be equal to number of rows of the second matrix. In such a case, we say that the product A into B is defined. So, when A into B is defined, if A into B is defined, if A is of the form m by n, B is of the form n by p, or in general, number of columns of the first matrix is equal to number of rows of the second matrix, and the result, we get a matrix that is of the form C equal to Cik, and its order will be of the form m by p. So it is entirely different from the concept of addition. Addition is possible only when the orders are equal. But the case of multiplication, the multiplication is defined or the multiplication is possible only when the number of columns of the first matrix is equal to number of rows of the second matrix. And this is true when we take the square matrices of equal order. That means here is a matrix 2 by 2 and another matrix 2 by 2. Number of columns in the first matrix, that is 2, and number of rows in the second matrix, that is also 2. That means without going for any calculation, we can say that square matrices of same order can be multiplied. We stress that 2 square matrices of same order can be multiplied. Let us take an example. 2 matrices which are not square matrices having the same order. A is a matrix, that's order is say 2 by 3. Another matrix say B, that's also of order 2 by 3. If you look at number of columns in matrix A, that is 3, whereas number of rows in B, that's equal to 2, where 3 is not equal to 2, so we say that A into B is not defined. So, A into B is defined for the square matrices having same order, and for all other matrices, it is possible only when number of columns of the first matrix is equal to number of rows in the second matrix. Let A is equal to matrix 2, 3, minus 1, 4, and B is equal to matrix 3, 0, 1, 2. We find the product A into B. A into B is equal to 2 into 3 plus 3 into 1. That is the first element. The second element is 2 into 0 plus 3 into 2. Here, minus 1 into 3 plus 4 into 1. Coming to the last element, minus 1 into 0 plus 4 into 2. We get 2 into 3, that is 6, plus 3. Here it is 0 plus 6 and minus 3 plus 4 and 0 plus 8. On simplification, we get a square matrix that is 9 6, 1, 8. It's of order 2 by 2. Now we find out the product B into A. Let B into A, that is 3, 0, 1, 2 into 2, 3, minus 1, 4. We get the product as 3 into 2 plus 0 into minus 1. Next, 3 into 3 plus 0 into 4. Coming to a second row, 1 into 2 plus 2 into minus 1. Last element, 1 into 3 plus 2 into 4. We find the answer as 6 plus 0, 9 plus 0, 2 minus 2, and here it is 3 plus 8. Further on simplification, we get 6, 9, 0, 11. Now look at both the products, A into B and B into A. A into B is equal to 9, 6, 1, 8, whereas B into A is equal to 6, 9, 0, 11. In this example, it's very clear that A into B is not equal to B into A. Whereas in the case of matrix addition, A plus B is equal to B plus A. That is, matrix addition is commutative, whereas the matrix multiplication A into B is not equal to B into A. That means the matrix multiplication is not commutative. Now we take two matrices A and B. Let A is equal to matrix 5, 6, 4, 5, and B is equal to matrix 5, minus 6, minus 4, 5. Let A into B is equal to 5, 6, 4, 5 into 5 minus 6 minus 4, 5. That is 5 into 5, 6 into minus 4, 5 into 5 plus 6 into minus 4. Going to the next column, 5 into minus 6 plus 6 into 5, and then second row, 4 into 5 plus 5 into minus 4, and next 4 into minus 6 plus 5 into 5. That's equal to 5 into 5, 25 minus 24. Here 5 into minus 6, 30 plus 30, and here 20 plus minus 20. Here minus 24 plus 25, and we get the matrix 1, 0, 0, 1, and it is of order 2 by 2. We look at the product B into A. B into A is equal to, B is 5 minus 6 minus 4, 5, and A is the matrix 5, 6, 4, 5. We get the product as 5 into 5 plus minus 6 into 4. The second element, 5 into 6 plus minus 6 into 5. Second row, minus 4 into 5 plus 5 into 4, and then minus 4 into 6 plus 5 into 5. That's equal to 5 into 5, 25 minus 24, 30 minus 30, minus 20 plus 20 minus 24 plus 25, and we get 1, 0, 0, 1. is of order 2 by 2. We compare the product A into B and B into A. A into B is equal to 1001 and B into A is equal to 1001. In this case, we find that A into B is equal to B into A. But in the previous example, A into B is not equal to B into A. There are cases where A into B is equal to B into A, but in general, we cannot assume that AB is equal to BA. That's the reason we say that the matrix multiplication is not commutative. Let P is equal to matrix 0, 4, 0, 5. It's of order 2 by 2. And Q is equal to matrix 5 minus 2, 0, 0. It is of order 2 by 2. We find the product P into Q. P into Q is equal to 0 into 5 plus 4 into 0, 0 into minus 2 plus 4 into 0. Second row, 0 into 5 plus 5 into 0. Next, 0 into minus 2 plus 5 into 0. On simplify, we get 0 into 5, 4 into 0, that is 0. 0 into minus 2 and 4 into 0, that is again 0. 0 into 5 plus 5 into 0, 0. 0 into minus 2 plus 5 into 0, that is also 0. And it is of order 2 by 2. Unlike the case of real numbers, we can find another property here. P and Q are two non-zero matrices, whereas its product P into Q, 0, 0, 0, 0, a zero matrix. That is, product of two non-zero matrices may be a zero matrix. In case of real numbers, when the product is equal to 0, we say that at least one of them is equal to 0. But in case of matrices, if the product is equal to 0, it does not imply that at least one of the matrix is a zero matrix. So this is a typical example where P is non-zero, Q is non-zero, whereas the product PQ is a zero matrix. So far, we find the product by taking the square matrices. Now let us take two matrices. Both are not square matrices. We try to find the product. Let A is equal to matrix 2, 1, minus 1, 4, 3, 2. We know that its order is 3 by 2. And another matrix, say B, that is 2, minus 1, 4, 0, 2, 5, and its order is 2 by 3. Let us see the multiplication is defined or not. A is of order 3 by 2 and B is of order 2 by 3. We see that these two numbers are equal. The resultant matrix AB is of order 3 by 3. Now let us find the product. A into B is equal to matrix 2, 1, minus 1, 4, 3, 2 into matrix 2, minus 1, 4, 0, 2, 5. We follow the principle of multiplication, that is 2 into 2 plus 1 into 0. The next element, 2 into minus 1 plus 1 into 2. We have got one more column to be multiplied, so it is 2 into 4, 1 into 5. Coming to the second row, minus 1 into 2 plus 4 into 0, minus 1 into minus 1 plus 4 into 2 Going to the third column, minus 1 into 4 plus 4 into 5. The last row, 3 into 2 plus 2 into 0, 3 into minus 1 plus 2 into 2. The last element, 3 into 4 plus 2 into 5. That is 2 into 2 plus 1 into 0, we get 4. Here 2 into minus 1 plus 1 into 2, we get 0. 2 into 4 plus 1 into 5, we get 13. Minus 1 into 2, that is minus 2 plus 0, you get minus 2. Minus 1 into minus 1 plus 4 into 2, that is 9. Minus 1 into 4 plus 4 into 5, you get 16. 3 into 2 plus 2 into 0, you get 6. 3 into minus 1 plus 2 into 2, we get 1. 3 into 4, that is 12, and 2 into 5, 10, that is 22. Exactly, we get a matrix of order 3 by.
Dear students, just now we learned how to multiply two matrices. We have also learned that for any two matrices A and B, A into B is not equal to B into A. Apart from this, we are going to learn a few more properties of matrix multiplication. They are associative law, distributive law, and existence of multiplicative identity. Let us see what is associative law. For any three matrices A, B, and C, AB times of C is equal to A times of BC whenever both sides of equality are defined. This property we call it as associative law. Next, distributive law. For any three matrices A, B, and C, A times of B plus C is equal to AB plus AC, and A plus B times of C is equal to AC plus BC whenever both sides of equality are defined. The third property, that is existence of multiplicative identity. For every square matrix A, there exists an identity matrix of the same order such that A into I is equal to A, and that's equal to I into A. So these are the three properties. We are going to prove it by taking examples. The first one, associative law. Let A is equal to matrix 1, 2, 0, 4, B equal to matrix 2, 3, 5, 6, and C equal to matrix minus 3, 2, 1, 3. We find A into B, that is matrix 1, 2, 0, 4 into matrix 2, 3, 5, 6, multiply it, we get it 1 into 2 plus 2 into 5, 1 into 3 plus 2 into 6, 0 into 2 plus 4 into 5, 0 into 3 plus 4 into 6. We simplify it and we get the matrix 12, 15, 20, 24. Now we multiply by C, that is AB times of C equal to 12, 15, 20, 24 into minus 3, 2, 1, 3. On simplification, we get minus 21, 69, minus 36, 112. We take it as equation number 1. We now calculate the RHS, that is A times of BC. For the three matrices A, B, and C, what you have taken earlier, BC is equal to matrix 2, 3, 5, 6 into matrix minus 3, 2, 1, 3. Multiply it, simplify it, we get minus 3, 13, minus 9, 28. We multiply by A, we get matrix 1, 2, 0, 4 into matrix minus 3, 13, minus 9, 28. Multiply it and simplify it, we get the matrix A times of BC as minus 21, 69, minus 36, 112. We take it as equation number 2. We now take the equation number 1, what we have proved earlier, that is AB times of C, which is also minus 21, 69, minus 36, 112. We compare these two matrices 1 and 2. we can say that A times of BC is equal to AB times of C. That is, AB times of C is equal to A times of BC. We now move on to the next property, that is distributive law. We take three matrices, A equal to matrix 1, 2, 0, 4, B equal to matrix 2, 3, 5, 6, and C equal to matrix minus 3, 2, 1, 3. We find A times of B plus C, that is matrix 1, 2, 0, 4 into matrix 2, 3, 5, 6 plus minus 3, 2, 1, 3. Add these two matrices and multiply it. We get matrix 1, 2, 0, 4 minus 1, 5, 6, 9. That's equal to matrix 11, 23, 24, 36. We take it as equation number 3. We now calculate AB plus AC. AB plus AC equal to 12, 15, 20, 24 plus matrix minus 1, 8, 4, 12. We get matrix 11, 23, 24, 36. We put it as equation number 4. We compare this 3 and 4. We can see that A times of B plus C and AB plus AC both are equal. So A times of B plus C is equal to AB plus AC. Existence of multiplicative identity. Let A is equal to matrix 8, 6, 3, 2, 4, 5, 5 minus 4, 7, which is of order 3 by 3. We consider the identity matrix of the same order 1, 0, 0, 0, 1, 0, 0, 0, 1. We now multiply A and I, or AI is equal to matrix 8, 6, 3, 2, 4, 5, 5 minus 4, 7 into 1, 0, 0, 0, 1, 0, 0, 0, 1. On multiplying and simplifying, we get 8, 6, 3, 2, 4, 5, 5 minus 4, 7, which is exactly equal to the given matrix A. So we proved A into I is equal to A. The same way, we can also prove that I into A is equal to A. We now move on to a few more examples which you have not discussed earlier. Let A is equal to 1, 2, 7, a row matrix of order 1 by 3, B equal to 4, 6, 1, a column matrix of order 3 by 1. Once we multiply this A and B, a matrix of order 1 by 3 with another matrix of order 3 by 1, we get a matrix of order 1 by 1. That is, A into B is equal to matrix 23 of order 1 by 1. We take now P equal to 3, 2, 1, a column matrix of order 3 by 1, and Q equal to 5, 4, 3, a row matrix of order 1 by 3. We multiply P and Q, we get a matrix of order 3 by 3. That is, P is of order 3 by 1, Q is of order 1 by 3. On multiplying 3 by 1 into 1 by 3, we get the matrix 15, 12, 9, 10, 8, 3, 5, 4, 3, a 3 by 3 matrix. With this, we conclude today's lesson, that is matrix multiplication. Thanks for watching.